What you've just listened to is the voice of the atmosphere, channeled through the latest installation put up within the Atmosphéries program. In this presentation, you'll be introduced to this long-running research creation program, but also to considerations about sensors, data to sound transposition, and spatio-temporal dimensions of in-situ installation art. Atmosphéries was born along a series of art science projects initiated by Nicholas Reeves and spanning about 25 years. Ever since its initiation in 1997, this research program has revolved around the design of medio-electronic instruments of architectural scale and specifically meant to convert, locally and in real time, the shape, density, and layering of clouds into sound and musical sequences. Altogether, 14 of these so-called cloud harps were built, each of them constituting a revised and evolved version of the previous one. Today, we will focus on the last iteration, which you've heard at the beginning of this presentation. It is called the meridian probe. Generating sound from meteorological phenomena is not an unprecedented practice. It can actually be done in a number of ways, and numerous attempts can be traced in the last centuries. A more recent example is that of Andreopoulos' work. In 2004, the environmental artist gained attention with her sonic installation Atmospheric Weatherworks. For this project, she collaborated with meteorologist Glenn Van Noo to sonify data related to two extreme meteorological events, both recreated through scientific weather models. A more common practice is to rely on an application programming interface, or API, like it was, for example, done in Michael Bezinski's project Weather Report. Using APIs facilitates data exchange between applications, so that meteorological data from dedicated services, in Bezinski's case, the American National Weather Service, can serve as a basis for the data to sound transposition. So, what distinguishes Atmosphéries and the Meridian Probe from such projects? Well, our first distinction is the intention behind the data to sound transposition. For Pauly, data to sound transposition acts as a complement to scientific research. The transposition becomes a new way to analyze the data. Pauly's work, in a sense, contributed to a finer comprehension of extreme weather dynamics. This analysis-oriented view is characteristic of sonification practices. It is not shared by Atmosphéries, whose primary intention is, as mentioned earlier, of poetic and artistic nature. The cloud harps should therefore not be assimilated to sonification projects. Another difference is linked to the data acquisition method. Atmosphéries draws its meteorological data from monitoring instrumentation that's directly embedded within the instrument. In Pauly's project, the data was not obtained on site, but through a theoretical model obtained with mathematical simulations. On the other hand, API-based projects are entirely digital. They rely on weather data sourced from the web, provided by remote, public, or commercial meteorological services, whose measurement methods are not always obvious. Atmosphéries' projects are fed by real-time data captured on-site and immediately processed by the embedded instrumentation. What is heard by the visitors corresponds to what happens to the atmosphere at the very same place, at the same moment, directly above and around the installation. Now you're probably wondering about the data acquisition method that Atmosphéries relies on, and that gives singularity to this program. What exactly is being measured? How do the cloud harps collect data? And how do we transform atmospheric data into compositional material? The Meridian probe is equipped with 3 different probes that contain 10 different meteorological sensors. For the sake of the present paper, we'll concentrate here on the one that's dedicated to cloud monitoring, the CT25K liter ceilometer from Vaisala. At the core of the ceilometer is an infrared laser whose beam points directly towards the zenith. Every 12 seconds, tens of thousands of short laser pulses are sent towards the sky. When they hit a cloud, the energy is dissipated along 3 different ways. A part of it crosses the cloud and is lost into space. Another part is diffused within the cloud, and the remainder is reflected towards the ground. This last portion, called the backscatter, is detected by a receiver within the ceilometer. From the pulse's time travel, the ceilometer computes the altitude of detected clouds. But clouds are not stable entities with hard edges. their boundaries are not easy to define, and they change constantly. So how does the ceilometer know that it has detected a cloud? Clouds are made of aerosols, very small water droplets suspended in the atmosphere. The ceilometer extrapolates cloud presence from the density of aerosols found at every altitude interval up to 7 kilometers. The so-called leader equation is at the heart of this operation. It gives us the strength of the backscatter received from a given altitude z. Basically, a strong echo, that is, a backscatter whose energy is close to that of the beam initially sent, speaks for a high droplets density and highly distinguishable clouds. On the contrary, a weak echo relates to a transparent atmosphere or to shallow clouds. The laser does not encounter any obstacle that would cause it to bounce back. The ceilometer transmits its processed data to the computer through formatted messages. Every 12 seconds, a message like this one is sent. It contains raw backscatter values at all altitudes, plus other data like the number of cloud layers detected. These messages are the basic material for the data-to-sound transposition. Therefore, adequate reception, processing, and interpretation of the sensor's data is a substantial part of the work in Atmosphéries. For this, we used the fairly known MaxMSP platform to develop our own cloud-to-music composition instrument, to which we gave the name Ithaca. Along the years, the Ithaca interface has become an extremely powerful and versatile instrument. This picture shows one of its interface windows. It allows the composer to map any kind of atmospheric data to any of the available musical parameters. This interface is divided in 3 sections. On the left is the section dedicated to the input, that is, atmospheric data. For instance, the data extracted from the ceilometer's messages comes in here. The central section is the data-to-sound matrix. By clicking on the small ellipses, the composer associates available atmospheric variables, like cloud layer height, wind speed, or air temperature, to musical parameters, like frequency, ADSR envelope, and so on. On the right is the sound-related section. It allows the musician to choose from 4 different sound-generating modules. The interface window displayed here allows to orchestrate sounds produced through a sampler. Equivalent windows have been designed for the 3 other modes. Through these endless arrangement possibilities, the sky can be divided into a series of voices. The atmosphere becomes like a choir, with voices entering or quitting according to cloud layers activity at different heights. Working with a device such as a cloud probe provides the composer with an almost unlimited potential for poetic expression. Yet, we quickly came to realize that unveiling the artistic potential of sensors comes with a counterpart. The composer has to deal with their own artifacts and limitations. Our first limitation to consider is that sensors only give us a discretized, skewed representation of the continuous natural phenomenon. Here, the discretization occurs first at the spatial level. The echoes received by the lidar correspond to 50 feet altitude intervals. The atmosphere is then vertically divided in a series of cells in which atmospheric conditions are considered homogeneous. The composer must remain constantly aware that what he hears while orchestrating the clouds is not the cloud itself, but its representation through the prism of a monitoring instrument. Other limitations are linked to the inadequacy of specialized sensors to specific artistic ventures. Creative solutions must be developed in order to bypass them. For instance, the ceilometer's probing delay of 12 seconds is far to be optimal for the musical objectives of the Meridian probe. A much faster data streaming rate is needed to create even the simplest musical sequences. To mitigate this problem, we implemented a fractalization algorithm based on Fonkor's famous curve in our MaxMSP interface. The advantage of this method is that it generates new data through interpolation of measurements coming from the measured cloud itself. Every iteration multiplies the number of values by 12, allowing us to increase the rhythm of the incoming data stream so as to suit the musical purpose of the probe. Here is the last version of the Meridian probe that was shown last summer in the gardens of the Bussy-Rabutin Castle in France. At the age of high-performance communication networks and connected objects, Atmosphéries instruments are singular entities. They allow the visitors to share an experience happening here and now, immersed in the never-ending fluxes of the atmosphere. Through the thin, linear laser pointing towards the zenith, the here is reduced to almost a single point in the sky. It's a high-resolution locality. This feature is specific to this technology. In this way, relying exclusively on the lidar for cloud data collection is in itself a manifesto in favor of radical locality. In conclusion, Cloud Harps and the Meridian Pro are a genuine proposition to reinstate the intrinsic in situ quality of former tech-free, authentic sonic experiences. Through all of our research, we came to realize to which extent the nature and characteristics of a given sensor impact not only the final representation of the probe phenomenon, but also the full sequence of operations that lead to the final artistic transposition. The specific technology and the interpretation algorithms of the CT25K lidar influence the data as well as the artwork to a much greater degree than was first imagined. It seems therefore essential to give our measuring devices the credit they deserve and to see them as actors and partners with their own identity and attributes. In the end, there is no other way than to accept their idiosyncrasies and to turn them into features that can potentially contribute to and even enrich the artistic result. Whereas these aspects can be seen as problematic when used for scientific or technological ventures, they open vast exploration territories for the artists who decides to work with them and to undertake with them a potentially fruitful collaboration. This is the end of this presentation. Thank you so much for your attention. If you'd like to know more about the Cloud Harps, Meridian Probe, or other activities of the NXT Gestation Design Lab, feel free to contact us. We'd be happy to answer to your questions and remarks. We wish you a pleasant AudioMostly conference. Goodbye.